Here's a puzzle simple enough to hand a 14-year-old. Find me a number that squares to -1. Go on. Try. You can't. Not on the number line you grew up with. The parabola just floats there, refusing to touch the axis. No solution. So, mathematicians did the most audacious thing they knew how to do. They didn't find the number. They invented it. They called it I. They turned the line into a plane and gave every number a partner. And once they'd done that, a rumour started going around. A rumour almost too good to be true. The rumour is this: take any polynomial you like. Any of these towers built from powers of a variable we'll just call z. Set it equal to 0. The rumour says it always has a solution. Always. A degree 2 polynomial has 2 roots. Degree 5 has 5. A degree 100 monster hides exactly 100 roots, somewhere out in that plane. No exceptions, no escapes, no polynomial anywhere that slips through the net. They gave it a grand name, the Fundamental Theorem of Algebra, which is a little bit of a joke, and I'll tell you why at the very end. But first, how on earth would you prove a thing like that? Now, your first instinct is the obvious one. Just solve it. You know the quadratic formula. Plug in, out, come the roots, done. And for a while, that's exactly how everyone assumed this would go. Find a formula, and the formula proves the roots exist by simply handing them to you. For cubics, a formula does exist, and prying it loose was a bloodbath. Picture Renaissance Italy, where mathematicians duelled in public for money and for jobs. A man called Tartaglia cracks the cubic and guards the method like gold. Cardano coaxes it out of him under a solemn oath of secrecy, then turns around and publishes it anyway. Tartaglia never forgives him. The quartic falls too to Cardano's own student. Degree 2, 3, 4, all of it conquered, all of it by formula. And then everything stops. Here's a perfectly innocent-looking equation. Z to the 5th minus z minus 1. Try to write its solutions using roots and fractions and powers, the way you did for the quadratic, and you will fail. Not because you're not clever enough, because it is impossible. A young Norwegian named Abel proves it and dies broke at 26. A young Frenchman named Galois proves it deeper still and dies in a duel at 20. Past degree 4 there is no formula. Full stop. So now we are genuinely stuck. If we can't write the roots down, how could we ever prove they're even there? Here's the trick. And it's beautiful. Stop trying to solve the polynomial and start watching it move. Think of your polynomial, let's keep calling it P of z, as a machine. You feed it a point z from the plane, and it spits out another point, P of z, somewhere else in the plane. Feed in 1 point, get 1 point. Fine. But we're not going to feed it 1 point, we're going to feed it a whole circle. Watch. As your input point walks once around a circle, the output point traces a loop of its own. And a root, a solution, the very thing we're hunting, is just an input that gets sent exactly to 0. To the dead center of the output plane. So the entire theorem, the whole question, collapses into one thing. Does that output loop ever hit the center? Let's start as small as we possibly can. The polynomial z squared. Feed it a circle of radius 2. What comes out? Squaring doubles every angle and squares the radius. So the output is a circle of radius 4, and here's the crucial part. It goes around the center not once, but twice. Watch that little counter, 2 full loops. We say the output has winding number 2. It wraps the center twice, and that number is no accident. Feed z cubed a circle, it winds 3 times. Z to the 10th. 10 times. The winding number of the output equals the degree of the polynomial. Hold on to that, and it's the whole ball game. But wait. Real polynomials aren't just z to the n. They've got all that clutter, the lower powers, the stray constant. Doesn't all that junk ruin everything? Here's the resolution, and it's lovely. Make the circle enormous, because when z is gigantic, the highest power utterly dwarfs everything else. Say z has size 1,000,000. Then z to the fifth has size 1,000,000 to the fifth, a 1 followed by 30 zeros, while the next term down is 1,000,000 times smaller than that. It's a stadium floodlight standing next to a birthday candle. The candle is simply invisible, so on a big enough circle the polynomial behaves exactly like its top term, z to the n, and its output loop winds around the centre n times, clean as anything. Picture a monster of degree 1 billion. Its output would lasso the origin 1 billion times, a coil wound so tight it'd look like a solid disc. The point is simple. Far out, the winding number equals the degree, and it is definitely, emphatically not 0. Now, what happens if we shrink the circle instead? Shrink it. Make the input circle tiny, a pinprick around the centre. Now every z you feed in is almost 0, so p of z is almost just the constant term, whatever the machine spits out when you feed it 0. The output is a little loop, huddled around that constant, sitting off away from the centre, and a tiny loop that doesn't enclose the centre. How many times does it wind around it? 0 times, unless that constant is itself 0. But then 0 is already a root, and we were done before we started. So look at what we've got. Big circle wins and times. Tiny circle wins 0 times. Same polynomial. And in between? In between, we slide. Let the circle shrink smoothly from enormous down to almost nothing, and watch the output loop deform continuously from that n times coil down toward the tiny nothing loop. The winding number has to travel from n all the way to 0. But here's the thing about a winding number. It counts whole loops. It is always a whole number. You can wind around 3 times or 4 times, but never 3.5 times around. It cannot drift. It can only jump. And to jump, the loop has to snag. Think about it. The only way a loop can go from wrapping the centre to not wrapping the centre is to pass straight across the centre itself. To break free of the pin, it has to touch the pin. So somewhere, at some radius between the enormous and the tiny, the output loop must pass right through the centre. It must hit 0. And the input point that landed there? That's a z with p of z equal to 0. That is a root. We never solved anything. We never wrote down a single number. And we proved a root has to exist, cornered it, forced it into the open, purely by watching a loop refuse to unwind. Gorgeous, isn't it? Now I have to be honest with you, because this is the part that separates a good story from a proof. Everything I just showed you is a picture, a wildly persuasive picture. But the loop has to snag on the centre to change its winding. Did we actually prove that? Or did we just draw it convincingly and nod along? Because you could imagine checking it. You could feed 1,000 polynomials through the machine, 10,000, and watch every last one snag right on cue, every output loop catching the centre exactly as promised. And you'd feel certain. But certain isn't proven. There are infinitely many polynomials, and no pile of examples ever closes that gap. It is only proof that counts. And the man who understood this better than anyone found this exact idea slippery. In 1799, a 22-year-old named Carl Friedrich Gauss writes his doctoral thesis, and he opens it by tearing the earlier attempts to shreds. D'Alembert, Euler, Lagrange, all of them. Decades of celebrated proofs that Gauss calls illusions, each one quietly assuming the very thing it was supposed to establish. And then Gauss offers his own, built on 2 curves crossing in the plane, a close cousin of the loop you just watched. It's brilliant, it's convincing, and buried inside it is a geometric assumption that these curves coming in simply have to cross, that Gauss draws but does not prove. The gap in his very first proof isn't properly closed for over 100 years, so Gauss does something telling. He proves it again and again. 4 different proofs across 50 years, the last one on the golden anniversary of the first, as though he could never quite stop making sure. And the cleanest early version of the growth idea Big Z, top term wins, doesn't come from a famous professor at all. It comes from Jean-Robert Argan, a bookkeeper in Paris, an amateur who ran a bookshop and did mathematics on the side, and who gave us the very picture of the complex plane we've been drawing this entire time. The theorem's cleanest thread runs through a shopkeeper. And that grand name, the Fundamental Theorem of Algebra? Here's the joke I promised. Every proof of it, Gauss's included, ours included, secretly reaches outside algebra. They all lean on the shape of the plane, on continuity, on the fact that a loop can't jump, on geometry, on motion, on the topology of the thing. You cannot prove the fundamental theorem of algebra with algebra alone. Something, somewhere, always has to move. And maybe that's the part worth keeping. Not that the theorem is useful, though it is, everywhere, but that a question a child can ask, is there always an answer? Pulls a bookkeeper and a boy genius and 200 years of stubborn, quarrelling brilliance into the same simple picture. A loop, turning around a point, unable to let go. We went looking for a number we could never write down. And instead, we found a reason it has to be there. Sometimes, that's the more beautiful catch.